Good morning, sir. My name is Marcia, and with my partner, Caren Cornelya, we are from IE Batch 2022 Morning Class 2, and we will be presenting partial and directional derivative.
So this is our presentation outline. First we have partial derivative, which will be explained by me, and next we have directional derivative, which will be explained by my friend Marcia. So let's start off with partial derivative, which is a function of two or more variables with respect to one variable, the others being treated as constant. So in the multivariable calculus, we have the function of two or more variables such as z equals to fxy, and we're dealing with a three-dimensional surface in space, where each point on the surface corresponds to a particular combination of x and y and the value of z, and that point is determined by the function of f. Okay, so now moving on to the notation itself. So consider a function of two variables, fxy, where x and y are independent variables, and the delta represents a partial derivative. So here you can see delta z over delta x, and this represents how the function changes with respect to changes in x while keeping the y constant. And the same is for delta z over delta y, which represents the rate of change with respect to y while keeping the x constant. Okay, so let's move on to the formulas now. Here you can see the two formulas on both pictures, on the right and the left. And here you can see that on the left, which is fx xy, it's a derivative of f with respect to the x, and on the right side, which is fy xy, is a derivative of f with respect to y. And you can actually add a second derivative as shown below, which is fxxy, where the first derivative, the one closer to the f, is paying respect to x, and the second derivative is also paying respect to x. And this works likewise within the y respect as well. So what you need to do with the formula is basically you just find the derivative of whether you're paying respect to the x or the y, and you keep developing on that if you want to find the second derivative. Okay, so let's move on to the first example we have, which is fxy equals to 9x squared minus x cubic y squared plus 2y to the power of 4. Now, what we need to remember, as you can see on the right, I've already given a formula, which is x power to n. So here, the n has to come down, which is n times x power to n minus 1 times x accent, and that's how you find the derivative. And you can see a few examples given below. So we're going to apply that to the question that we have. For example, if we're looking for f with respect to x or fx, it equals to 18x because the 2 comes down, and times with 9, which is 18, and x power of 1 because x power of 2 minus 1 minus 3x squared y squared. And here the 2y power of 4 is actually gone because we don't have to pay respect to x in that. And the same goes to the fy as well. And if you want to find the second derivative, or fxx, you just need to find the derivative again from the fx that we found before. So here the 18x becomes 18 minus 6x y squared because the x squared is the 2 comes down, becomes 6, and the x becomes 1 because 2 minus 1. And the same goes to fyy as well. Okay, so now we are going to try and plot the graph using a website called GeoGebra. And here I'm using the fx, which is 18x minus 3x squared y squared. And what the numbers I'm going to put is that x equals to 0.5 and y equals to 1. So we just need to replace the x and the y with the numbers that we want. And the result I got while counting manually by myself is 8.25. And I inputted the same formula as well as numbers and the GeoGebra, and here we can see the graph plotted, and this one was to respect to x, and the result is the same with the manual calculation as well. Okay, so moving on to the next example, which is z equals to e power to x squared y power to 5. And here you need to remember that if it's e power to n, it equals to e power to x times x accent. And there's also a few examples given below that. So what we need to do is just apply the same method to the question that we have. Hence, for the solution in respect to x, we have ex squared y power of 5, which is the same, times 2xy power to 5, which is basically the power 2, and we find the derivative of that. And the same goes to for the respect to y, which is e power to x squared y power to 5 times 5x squared y power to 4, which is the derivative of the y power to 5. And this is the last example, or example 3, which is z equals to ln x cubic minus y squared. And there's also a few formulas that you need to remember on this for the derivative of ln itself, which is if it's ln x, then it will equal to x accent over x, and there's also a few examples given below. So let's apply this to the question that we have. Since we have for the power for respect to x, we have x cubic, so we're going to find the derivative of that, which is the 3 comes down, and the x becomes x squared because x cubic minus 1 over the x itself, which is x cubic minus y squared. So that's the answer for the one respect to x, and we're going to apply the same method for the y, which is here we have minus y squared, and the 2 comes down into minus 2y over x, which is just the same with the respect to x. So those two are the answers we will get for respect to x and respect to y for ln.
Okay, now I'll be explaining about directional derivative. Previously, in partial derivative, we have fx and fy, where fx values are in respect to x. All variables that are not x will be constant, and the function changes in x direction. Same with fy. All values is in respect to y, when all variables that are not y will be constant, and the function changes in y direction, as can be seen at the image at the left side of the slide. Here, for x in respect to x and y in respect to y-axis. Now, what if we want to move in the direction of some other unit vector, so that it can be changing direction from any point and it has a slope? This will be called directional derivative, which is a derivative in a particular direction in the xy plane. For example, at the right side of the slide, we have here vector u at the point a comma b, which is not at in respect to x or in respect to y, but in the point of vector ab. Okay, so this is the formulas for directional derivative. At x comma y, duf or directional derivative at vector u is equal to fx times a plus fy times b. Fx and fy is referring to the partial derivative, and a and b is referring to the point from the unit vector u. Or it can be written in the dot product format, which is duf is equal to vector ab times vector fx and fy. Since the vector ab is equal to vector u, and vector of fx and fy is equal to nabla f, this symbol is called nabla, which is the vector from partial derivative fx and fy, then we can also put duf is equal to vector u times nabla f from the function fx comma y. And sometimes from the question, we're not given a number format of point from ab for vector u, but we're instead given a theta value or pi value vector. We can search the value of a and b by doing cos theta and for a and sin theta for b. Okay, so the first example question, find the directional derivative of fxy equal to 5x squared minus 2xy power 2 3 in the direction of the vector 1 over 2 comma root 3 over 2 within the directional derivative at the point 2 comma minus 3. Okay, so this is the answer. First of all, we need to find the partial derivative of fx and fy from the function fxy equal to 5x squared minus 2xy power 3. Fx will become 10x minus 2y power 3 and fy will become minus 6xy squared. And then we need to evaluate the values at the point of 2 comma minus 3 so that the x will become 2 and the y will become minus 3. For fx, we need to put the value of 10x minus 2y power 3 with x being 2 and y being minus 3. And by this calculation, we got the value is 74. Same with fy, we insert x2 and y minus 3 into the formula of minus 6xy squared so that it became minus 108. And then after getting this point, we need to find the result from the directional derivative of d vector uf equal to fx times point A plus fy times point B, which is 74 times 1 over 2 plus minus 108 times root 3 over 2. So it became 37 minus 54 root 3 or 37 minus 93.53 equal to minus 56,53. There is a note that if duf is greater than 0, then fxy is increasing in the direction of vector u at a, b. But if duf is below 0 or less than 0, then fxy is decreasing in the direction of vector u at a, b. And since this is negative, which means less than 0, we know that the function of fxy equal to 5x squared minus 2xy power 3 is decreasing in the direction of vector u at 1 over 2 comma root 3 over 2. By using the GeoGebra website, I can put the values from the question fx comma y is equal to 5x squared minus 2xy power 3 at the point of x equal to 2 and y equal to minus 3, and at the vector u, since a comma b is 1 over 2 comma root 3 over 2, we know that cos something equal to 1/2 while sine something is equal to root 3 over 2 is 60 degrees, so I put the angle of 60 for vector u, and we can acquire directional derivative of duf is equal to minus 56.53, which is the same as our calculation. And this is the graph for the question. Next, the second example question. Find the directional derivative of fxy equal to 2x power 3 minus 5y power 2 in the direction given by the angle theta equal to pi over 6 within the directional derivative at the point minus 2 comma 1. Okay, so this is the answer for this second question. We just need to do the same thing as the first question. So first we need to find the fx and fy partial derivatives of fxy to x power 3 minus 5y squared. Fx will become 6x squared and fy will become minus 10y. Now we need to find the value for fx and fy at the point minus 2 for x and 1 for y. Fx will become 6 times minus 2 squared or 6 times 4 equal to 24, and fy will become minus 10 times y, which is 1, which is just minus 10. And then since we are not given a true number, but we are given at vector pi over 6, which is 30 degree, we need to find a vector point for a and b. For a, we need to find cos theta, which is cos 30 equal to root 3 over 2. And for sine theta, we need to find sine 30, which is 1 by 2. And then just as usual, we need to put the values into duf, which is fx times a plus fy times b, which is 24 times root 3 over 2 plus minus 10 times 1 over 2, which became 12 root 3 minus 5. Or we can use calculator and it became 15,78 7846. And as previous, we have a note that since it is a positive value, we can say that fx comma y is increasing in the direction of vector u at pi over 6 or at 30 degree. Okay, so by using the GeoGebra website, I can put the function of fxy to x power 3 minus 5y squared at x at the point x minus 2 and y equal to 1 and at the angle of 30 degree. It is written here that the directional derivative is 15.78, which is the same as our calculation, and this is the graph. That is all from our presentation. Thank you for listening and have a nice day.